All right. Hi, guys. So welcome to the Colloquium talk. I'm very glad all of you are here. It's my great pleasure to introduce Dr. Glenn Hurlbert as our Colloquium speaker for the day. So Glenn's been a longtime mentor, collaborator, and a friend. He's also both professor and department chair in mathematics and applied mathematics at Commonwealth University. And he'll be speaking on a class of network optimization problems in graph theory known as graph pebbling. So despite knowing Glenn for very long, I know next to nothing about graph pebbling. So I'll let him take over from here. Thanks a lot.
Good. Thank you, Vikram. And thank you all for having me. It's kind of fun to continue to do this stuff when we can't travel, but it's good to see familiar faces. And one of the things that Vikram and I have been working together in extremal set theory for years, and so when we thought of talking, it just seemed natural that I might give a talk on the stuff we're doing. But I thought, no, he doesn't know this stuff, and you probably have heard him speak on that. So we went this direction. Liliana Alcon is the co-author that I've been working with for a decade or so. She's down in Argentina at the National University of La Plata, which is just south of Buenos Aires. And so let me give you a sense for what this stuff is. It's basically sometimes there's this whole class of problems that we just call moving stuff around on graphs. And you've got stuff sitting on vertices and you want to move them around. You have some rules for doing it. You have different objectives for doing it. And so in this particular variety, we start with this configuration, which is in green. It's just a function on the natural, on the vertices to the natural numbers. So I've drawn that in green here. These are pebbles. So the function value at this particular vertex would be 3 because it has 3 pebbles sitting on it. We also have a target. So you can think of configurations as the source of some commodity, and the target is a sink, right, or a demand. And it's the same thing. It's just a function on the vertices, but just to tell them apart, I'll use this, just the numbers. So here there's a demand. Somebody lives at that vertex and wants 2 of whatever you're selling, and you've got to try and move them there. We count the size by just counting up the number of pebbles or how many total demands we have. So the demand size would be 3. Configuration size looks like 11, I think, pebbles. So how this works is that you're allowed to move them, but you have to pay a cost. So in some of these moving stuff around in graphs, if you're doing network optimization traditionally, you can move them, but you have to pay some cost, $20 per package or some such thing, right? Here, you pay with the commodity itself, sort of like an oil tanker is using its own fuel, or electricity sometimes dissipates along a wire. Ideas like that. Back in the days of faxes, you send a fax 3 times and you can't read it, right? So there's information loss. So these are sort of vague models in that area, although I'll explain a bit as to where this model actually came from. So what we do here is we're moving along edges. So this would be a pebbling move, the notation for it, from U to some neighboring vertex V. So that squiggle notation is adjacency. What you do is you first pick up 2 pebbles from one vertex and move them to another one, but only one of them arrives. So you do these 2 at a time, and it's like you pay this toll, right? Some gremlin comes up and steals one. I used to think of this as, bootlegging through the forest, the woods, and the cops, when they catch you, they don't arrest you, they just take half of your liquor. So just reminds me of my college days, I guess, in North Carolina. But that wasn't a proof, by the way. So anyway, you would move 2, like these 2. And when you get there, one of them's gone. So that's the idea. What you're trying to do is have a sequence of pebbling moves. So I'll just call them, sigma 1 through sigma j. And so you could think of these as operators, and the product of those operators gives you some resulting configuration. And you want to make sure that you've got enough pebbles that were demanded at each vertex. Okay, so that's the whole idea. And here you could imagine accomplishing that by, maybe you would immediately move those two to put one pebble there, and the other would come here, right? So you've satisfied that 2. Now how are we going to deal with the 1? Well, without taking too much time to actually move those pebbles, you know that there's only 1 left there now, right? So you could take 2 from there, and now combined with the 1 that's already there, you have 2, which you can move to here. That gives you 2 there, and now you can come across to there, right? So if you're thinking naively about just checking all possibilities, you immediately encounter combinatorial explosion, as you can imagine, that you have to be a little more clever than just checking all the ways you can think of. But that's the idea, and the word we use is solvable. So for that target distribution D, we have solved it from this particular configuration C. Okay. If I had started from a different configuration of the same size, this green one still has 11 pebbles. But I can quickly see that it's impossible to solve D, because if I look at the only places where we have what are called big vertices, is what we call them, because they have more than 1 pebble. And you're only able to start making 2 moves, right? And so I'll never be able to put 3 things somewhere if I can only start moving 2. You never can increase the number of moves you can have available to you. And so already, without having to try many things, I'll know I'll only be able to solve at most 2 targets, and I have 3 to do. So that's, one of the sort of basic notions to think of, and we call that potential. So this word potential here is counting the number of disjoint pairs of pebbles that sit on the same vertex. So there's a pair there and a pair here, and that's it. So you need to start with some potential. It's, we'll steal all the physics vocabulary we can here. So that's one idea. And what we're looking for is this notion of what's called the Pebbling number of the graph for that target D. It's the minimum number of pebbles M, so that every configuration of size M can solve D, right? So here I know that I need more than 11 pebbles. Even though there was a configuration that did it, if I instead had this configuration, I'd be stuck. So I would need to buy more pebbles to start. You can think of it in an adversarial fashion. I buy the pebbles and give it to my enemy, and my enemy tries to prevent me from solving, right? So I need to buy enough pebbles that that's impossible for my enemy. And that's the Pebbling number. Initially, the model came out of an application where we just had 1 target. That's all we had. And so I'll get into that in a moment. This notion of not having enough potential, we call it small. Just, some nice jargon to keep people from understanding us to begin with. So small comes into play later, and there's some nice conjectures I'll share with you about small ones. Okay, seem okay so far? Feel free to stop me, and say what. You know how it is when you think you've said something and you haven't. But anyway, so let me tell you a little bit about where this model actually came from. It wasn't an optimization model to start. It was actually a number theory problem. Going way back, there was a question of Carmichael numbers when those were found 100 and some years ago as counterexamples to Fermat's primality test. And so there was a question about, are there infinitely many of these? Because it's still a pretty good test if there are only finitely many counterexamples. So it was around the 50s that Erdős had an idea of how to prove the infinitude of these Carmichael numbers. And it had to do with these things called zero sums. And with that idea that he couldn't press into a proof, suddenly it developed this cottage industry of zero sums. And through the 60s, you just find incredibly great research, very rich set of theorems about zero sums of all sizes and types and shapes and what have you. So in this particular one, again, you can think of it as a game that you pick some integer n, little n, and somebody hands you n integers. They could be positive, negative. I've written them as positive or zero. It doesn't matter. And so what you'd like to do is find some sub collection of those, and the numbers don't have to be distinct either. You can have repeats. So you'd like to find some subset of the indices, some collection, so that when you add up all the numbers, it's a multiple of n. This is a really nice, just stop right there, and it's a nice problem that I often give to students, when we're teaching the proofs class, for example, because it's a pigeonhole idea, and it comes from an idea they've already seen in calculus just on subsequences, right? When you look at partial sums out of calculus, right? You're always studying these things. And if the partial sums hit a zero somewhere, mod n, you're done. And if they don't, well, then pigeonhole says two have to be the same, and you've found a subsequence that's 0 mod n. But there's this extra condition floating around that seems like just completely random. Who cares about that? Where'd it come from? So what you're trying to do is look at the common divisors with n of the individual numbers and add those up and hope that that's not too big.
Glenn, can I ask a question?
Mm-hmm.
Isn't, if you set all the AIs to 1, isn't that a solution?
Yes, but you don't have control over that. Somebody hands you. So it has to be for all choices. Yeah.
Gotcha.
But that's true. And that's an extreme case of if somebody gives you n minus 1 ones, then you can't find such a solution.
Gotcha.
And so that's a nice thing that you bring up because it gives you the lower bound on how many that you have to start with. And right there you see a little bit of similarity with the Pebbling that you're looking for. How many do you need to be successful? So this question, Danny Kleitman and Paul Lemke had first proved this in the 90 or so. So it's sat around for 20 some years. But it was Fan Chung who used Pebbling to prove it. And it was really an idea of Ligarius. And so Jeff Ligarius and Mike Sachs had thought of building this graph model that I'll show you in a little bit to solve this problem. So it was really kind of neat, a surprise solution. And this generalizes. So zero sums can go into many different playgrounds. You can do them on abelian groups. So if you look at the size of the group and you take elements of those group of that group with repetitions possibly. Again, you're looking for a sub-sequence. I don't like to say sequence really because it's not ordered, but it's some sub-collection that sums to the identity of the group. And this part looks a little different, but it's really the same. If you divide by n, you get 1 on the right, and then the left side is 1 over the order of the group in the cyclic group, which is what you're doing in mod n, right? And so Alfred Geroldinger had proven this in the mid-90s, and a student of mine, Sean Elledge, and I were able to use Pebbling to prove that. And you can get more general than this, but that's not the point here of the talk. So, but it gives you a sense of some of these things. And in fact, that sum on the left turns out to be something called the cross number, that people who do factorization theory and work in monoids and these kinds of things, for them is a very important important computation to make, and they're interested in small cross numbers. So here it now gives a context of connections to other areas of algebra. Kind of surprising, but really nice. So let me give you just a couple of pictures, give you an example of, just to get a sense for what the connection really is. So let me start with this number n, and I'll give you maybe a minute or two to just factor it in your head. Okay, good. You got it. I know some of you were off by 1, but that's okay. So that's the factorization. And what we're going to do is we're going to just look at the divisor lattice, but we'll put it upside down. So what's the structure here is that you can see that 5 is the green number, and its multiplicity is 3. And so that gives me this vertical dimension. Vertical, who cares? It's a dimension. Those are my green length 3. Can't think of a good word for that, but that length direction. 11 shows up once, so there are all the 11s in parallel. And then 31 shows up twice, so that's length 2 in that third dimension. And so every divisor of n is 5 to something, 11 to something, and 31 to something. And so that gives you these coordinates. So this number corresponds to the number 1, and this is the number n itself. So that's the divisor lattice. What we're going to do is use this as our graph to pebble in. And without getting too technical, we're interested in getting 1 pebble at the bottom. So just believe me on that part. And the pebbling model here is a little bit different. Instead of taking 2 pebbles and losing 1 along the way, on the green direction, it's going to require you to take 5 pebbles, and still only 1 arrives. It's a heavier cost, right? Greedy cops. And here it'll take you to move along the purple dimension. It'll take 31 cases of beer just to get 1 to the party, okay? So that's a really hefty cost. All right. Now, where does the configuration come from? Well, as we noted before, someone is going to hand me 1,321,375 integers, okay? And I've got to comb through them. I'm going to turn each of those numbers that I'm handed into a pebble. And that pebble is going to have a home in this graph. It'll belong somewhere. So for example, if they give me this number, 2,984,850, that's a pebble. Where does it go? Well, again, I can give you some time to factor it, but this one's twice as big, so I won't make you do that. But here's the factorization. Most of it I don't care about. I only care about the factors that shares in common with n, because that's really what the problem is asking about, right? Common factors. So I look at the exponents of those prime divisors, and that tells me where it lives, right? I go 2 in the green direction. From here, 2 down is at this level, and then 1 in the red direction, right? So now I'm over here, and I don't go any in the purple direction. So that's where I live. All right, so somebody gives me all these numbers. They naturally find their homes in this lattice. That's my configuration. With these very costly pebbling moves, I have to get to the bottom. And what a pebbling theorem would do is say, you got enough pebbles, that's possible, right? The rest of the work has to do with, well, how does it, from the number theory sense, translate back, right? It's like a lot of math. You translate the problem into this area, you solve that, but you still got to translate it back. Well, I kind of got to skip that. You have a question? Oh, sorry. So, so does that make sense? There is a way that if I had, let's say, 5 pebbles here, and I was able to move one of them down to here, that I'd have to do so to preserve some number theoretic meaning. And especially that second condition, not just the zero divisor, but that second one of the sum of the orders, I have to pay close attention to. And that'll take, again, that'll stray us from what we really want to talk about today, or at least what I want to talk about today. Okay, but it can be done. What really happens is that I sort of think of it as like the nested Russian dolls, that when I find 5 pebbles, well, any 5 pebbles that happen to be sitting there, I find some sub-collection of them that has a nice property. I put them inside of one doll, and I move that doll down to here. And now that doll acts as a pebble or a number. And then it combines with other dolls of its size and gets put into another Russian doll that might, move that way. It had 10 other dolls with it, right? So it's that kind of thing. It's a little bit technical and complicated, but anyway, this is the translation of where pebbling comes from and how it's used in that regard. The other thing is that I can take any lattice like this and I can embed it in the Boolean algebra, or the binomial cube, if you think of it as. So here's a 4-dimensional cube, and I can find structures in it like this. Like instead of 2 times 2 times 2 times 2, which is, if you've been to the 4th dimension lately, you'll recognize it. Where do I find 3 times 3? And you can kind of see it there in purple and green, but to make it a little bit easier, I'll erase all the blue. And there it is. It's a grid, 3 by 3 grid. And so it turns out that any partition, divisor lattice like that, any product of paths fits inside of some large enough dimension cube. And it does so in a nice homomorphic way that it's called a retract. And what the retract does is allow you to use an answer to the cube to answer the lattice problem that you started with. So I'll gloss over that as well, but it's just the notion that I can reduce the problem, or this is Chung's approach. Ven Chung found this idea to use retracts to answer the question. So now she only has to answer, this one problem on cubes, okay? And she was able to do it, and blah, blah, blah. Happy days back in 1989. What it led to, though, is something called Graham's conjecture. So I was in graduate school at this time, and there was a nice meeting in DC that I know I'll bet you Andrew was there. And so Danny and Fan and I were, and Dan Ullman too also joined us, and we were sitting there having lunch and talking about this problem. And they're just, you know how it is, napkins everywhere, and then you miss the next talk. And and then a month and a half later, Fan had the solution. But hidden in this paper is a tiny little comment of Ron's that had this problem. If you know the Pebbling number, and this is just for one target now, because that's all the problem was at this point. If you know the Pebbling number for one graph G and the Pebbling number of the other graph H, is it true that their product is an upper bound on the Pebbling number of their Cartesian product, which is like the cube? You just join two copies together in parallel. Because if that question is true, and you think about it, maybe it's got an easy answer, then you get Chung's theorem instantly, instead of all the hard work that she did. Well, of course, that problem turns out to be a little bit hard. We think of it as the holy grail of the subject, and there's been, you know, a lot of literature on it. So it's true for some long list that I'm not going to dare to start. But still nowhere near, you know, no end in sight of somebody thinking, oh, here's how we should do it. And it's a matter of carrying out the theme. In fact, here's a graph that turned out to be very important early on. It's called the Lemke graph. Paul Lemke works out at IDA in San Diego, and I worked out there some with him. And I remember telling him that there's a graph named after him now, and he was quite satisfied. And it has to do with the technique that Fan used in her proof. Required a special property. And Paul found this smallest graph without having that property. And so I some years ago offered not the $64,000 question, but it's just the $64 question. Is the Pebbling number of the product of that graph with itself equal to 64? My sense at the time was maybe not. Maybe actually Graham's conjecture is false, because the Pebbling number of this graph is 8. So that's been sitting around for a long time, and the best bounds, my first bound was in the hundreds, 108 or something. We got it down to 96, and I think it's into the 70s now. It's doing better, but no one's even close to that. You think, how hard can that be? It's just a graph on 64 vertices. Well, once you ask, well, how hard can that be? Of course, we're talking about complexity, right? So let me say a thing or two about complexity. Hal Kierstead and I, and then after that, Kevin Mylans and Brian Clark, proved that in general, just having a configuration and a target on some arbitrary graph, you can't answer the question, is this solvable in polynomial time? Unless you're lucky. But in general, you can't. Well, you know, P equals NP, blah, blah, blah. So, so it's tricky. One of my favorite results, Chuck Cusack up at Western Michigan, it turns out that he proved if you restrict to just planar graphs, it's still NP complete. If you restrict to diameter 2 graphs, it's still NP complete. But if you restrict to planar and diameter 2, now it's polynomial. I just love that. It's sort of right on the border there. It's a beauty. So we start to ask, you know, for what graph classes is it polynomial? I won't explain what this is, but if you're trying to find upper bounds, that's a much harder problem, right? If you can't even decide whether something's solvable, how are you going to get the Pebbling number? So this has to do with being allowed polynomial number of NP complete questions. You've got some oracle in a black box with you. And you can say no instead of yes. So anyway, it's technical, but it's harder. So our conjecture with Liliana and also another colleague, Mauricio Gutierrez, down in La Plata, have been building towards this conjecture that if you have a pyramid-free chordal graph, which I have to say a little bit about what that is, then it's a polynomial question. So here's the pyramid, right? I guess it's as close as a graph can be to looking like a pyramid. And that pops up in some areas of graph theory, just, sort of like Peterson does, right? It's in graph structure that pops up a lot, and it's coming up here for us. Chordal means that every cycle has a chord, well, cycle of length 4 or bigger. So for example, here are 4 vertices that form a cycle, and there's a line cutting through it, a chord, right? So that's what a chordal graph is. They have wonderful properties. They have these things called simplicial vertices. That corner is a simplicial vertex. The reason it is because when you look at its neighborhood, that is the vertices it's adjacent to, they form a complete graph, meaning that they're all adjacent to each other. And so that makes it simplicial. And the miracle of chordal graphs is an old classification theorem that says chordal graphs have simplicial elimination ordering, meaning I can remove that vertex. It's still a chordal graph because you can't create chordless cycles by removing vertex. And then you can remove another one and so on. You iterate, it sort of decomposes that graph. And you can use that to great effect, that kind of structure. So that's our conjecture, and some things are known about it. Chung in the first paper, unwittingly proved it for trees. She gave a formula, and you had to do some work to partition the tree in such a way to figure out what the formula is. Diameter 2 graphs, it's true for. They're not chordal, but that was an early result of a polynomial class. All of these are chordal. We've been the last decade working on these. We didn't have this portion of it until recently when we started to do some types of trees, but that I won't describe. Okay, in trees, what Chung was looking at is relationships between pebbling numbers from one place in the graph to another. If I'm going to try to get one pebble to the vertex V from this schematic diagram of a tree, then if I remove that vertex and just look at this much, t minus v, it's equivalent to getting 2 vertices to W, because that's what's going to take to move from W to V, right? So that kind of gives you one relation that you can use in building some inductive idea. For vertices that aren't leaves, similarly, you can look at its neighbor is sort of the root of some other tree and so on. And, ignore this actual formula. But the idea is that once I've said, oh, I better study this more general pebbling number of getting 2 targets somewhere, I better start answering that because I'll have to use that inductively. And so it's a way to, inductively look at the tree and strengthen the theorem you're trying to prove so that you can use that inductively. So, okay, it works to do that. That's the sort of moral of that fact. Another is that trees are greedy. That means that you only ever have to consider walking towards the root, getting closer to it. In other graphs, that's less obvious and sometimes not true. So this concept of greediness comes into play. Other things you're often concerned about in solutions is how much it cost. How many steps did it take you? Because if you're going to lose one every time, you hope that it doesn't take too many steps. Because if you're going to try to solve many targets, once you solve one, you still want to have lots left over. So just measuring the cost of what what it took to solve one of them becomes something you want to keep track of, right? You can prove that greedy solutions have a cost that's bounded above by 2 to the diameter of the graph. And so there's the particularly nice ones. And since they're nice, we give it a name. We call them cheap. Exponential doesn't sound cheap, but maybe 2 to the diameter is still smaller than number of vertices or something. So anyway, these are the kinds of things that you kind of keep track of along the way. Here's an example of a tree and how you might partition it according to Chung's idea. If the root is at a leaf, which it's not too hard to argue that that's going to give you that'll be the most difficult one to reach. It's going to require the most pebbles. You'll look at the longest path from that root. And if it's length 9, as this is, you put 2 to the 9 pebbles except 1. And you won't be able to get there. Once you have that, you look at the longest path from some other leaf to this path. It's like a spine. You just want to get to, so there you have a length 4, and you see how many pebbles you should put there. And if that's what you have there, you know that you can never use an orange pebble to reach a blue path. And you iterate this process, and you get some formula for how many pebbles you actually used. And it turns out that just one more pebble is enough to solve it, and you use the ideas that we were talking about before. So it's just a typical mathematical trick that, centuries old, of generalizing the problem to make it easier to solve. Make the problem harder makes the proof easier, right? Kind of thing. Especially when induction's involved. What we want to talk about in this work is these graph powers. So you start with a path. In general, for any graph, what you're going to do is add edges to that graph to form the kth power, which is what this exponent means. So you'll add edges between vertices that currently have a distance at most k. So this is the path to the first power. You don't add anything because they already are adjacent. But the next one, so P2, you'd add edges between vertices that are distance 2 on that path. Distance 3 gives you more edges, and so on. Okay, and then it turns out that the formulas, they start to get a little complicated. And you just have to say, what case am I in? If I'm trying to get T pebbles, which is this notation, to some particular root, which let's take it on faith is the hardest one to do is at the end. This is a simplicial vertex here. That when, in some cases, that's your formula. In some cases, this is your formula. We have names for them. Ones we think of as wide-looking graphs, and some we call long graphs. And the difference between these two, you have to decide. The only difference is this much, and if you calculate it, you're making your decision on how T compares to this ratio here. So you've got this threshold that when T is small, you use this formula, and when T is large, you use that one. And it turns out some years ago, it was proved that all graphs have this property, that eventually, when T is large enough, there's some threshold where this term appears. And the rest is fixed, has no T in it. But lots of different things can happen along the way. You can get more than just 2 formulas. And in our work on split graphs, I think we had 6 different formulas. And it's tricky to kind of figure out. And in order to figure out, you had to find triangles and do stuff that required like cubic amount of work. So it's still polynomial, but like the tree, it took some time to decompose it. That turned out to be, you can do it in linear time, but sometimes it takes longer. So where do these formulas come from? They come from, here's one configuration, the wide configuration. You put a single pebble on all the interior vertices. That accounts for this much in the formula. You put this much at the end, which is one less than that term. And because it's small, we don't have enough potential. We can't put T pebbles on the root, on the target R at the beginning. There's another similar one where you don't put single pebbles everywhere. You put them n-2 except for these groups of k of them, and if d is the diameter, they're d-1 of those groups. You ignore those. But that allows you to put many more pebbles here, and it's not hard to show that then you can't put so many into that region, and you can't put, it just carries. So those sort of bounds are not hard. It's finding that finite set of extremal cases. You never know when you're done until you've got a proof of the upper bound. So there you have it. So the conjecture that we're leading to is one by, you start out with some notation like this. I'll just have to share with you. T is a number, V is a vertex. And so this particular configuration has a demand of T at that vertex and doesn't have any other demands. So it's sort of stacked, all my demands in one place. And the target conjecture that Dave Herskovich and Ben Hester and I made, I don't know, time flies. I forget, maybe 2006 or 8 or something like that. That if you're going to try to calculate the Pebbling number of a generic target, it's at most that of the stacked target for some vertex, whichever the worst one is, whichever has the biggest formula. So the stacked targets are the hardest to reach in a sense. In hindsight, it kind of makes sense. If you found the worst vertex to reach, you might as well make that the demand all the time rather than spread them out to easier ones. Roughly the sense of it, not the proof of it. And this has been in our early paper. We proved it for all the usual things you try at first, and then recently I have an undergraduate student, actually, Asak Sadiq, and we've done it for a couple of nice classes of graphs. So there's some new work coming along in that regard. But more recently, we found that the conjecture is probably weak, that we have a stronger version of it that we think is true. So here's the strong target conjecture. And in this one, we have to measure the support of a target, meaning that how many vertices are requesting or demanding a pebble, at least. So you're counting the size of the support of that function. And what we think is that's the weak conjecture, is that you can decrease the upper bound by the support -1. And so that's the strong target conjecture. And this is what we've just proved for these classes, trees, complete graphs, and this. The reason we're looking, by the way, at the path power is because this turns out to be a fundamental structure on the way to interval graphs, which gets you to trees, which is getting very, well, generalized trees, which is getting you close to general chordal graphs. So it's one of the building blocks along the way. All right, I don't have too much time, so let me point you to some of the main results, and you may have heard some of these results already in a different form. So the first two you might know. These were proved over the last week or so. So I can't tell. I don't know if that's the joke in the talk or not, but And actually, I'll tell you, when I first moved here to take the job at where am I again? VCU. I remember it was like the week before school started, and I'm at the department, and there's a couple of students hanging out front, I think 4. And so I was just chatting, where are you from? What year are you in? That sort of stuff. And one of the students said that she was from Nova. And I thought, oh, cool. And I'm thinking, oh, transfer student. And how about you? And the other person said, yeah, me too. And I thought, wow, 2 transfer students from Nova. That's interesting. Turned out they were all from Nova. And I was like, that's incredible. I can't believe you're all, what are the odds of that? And they looked at me like I was weird, because here in Virginia, Nova stands for Northern Virginia. So that's with a capital V. So I was like, no, that's, I guess, not high odds. But they had never heard of Villanova. I was like, who hasn't heard of Villanova? So anyway, it does lead me to a conjecture, though, that you might be interested in, that I think it might require a miracle. I don't know. So that's a very strong hypothesis, I would say. Anyway, here's the main theorem, and this theorem uses every technique in the book and some more. So all the generalizations that you might think of that we're gonna, this is the statement of the strong target conjecture. But here's something else, that if the graph is t wide, then there is some small configuration of maximum size that's unsolvable. So it's a structural thing. So it turns out we needed to add even one more, right? Make the problem harder. Again, that sometimes we're able to prove at some point in the theorem this first statement and use it to prove the small statement. And sometimes we need to prove that one and use it to prove the first one. So it's fun. It's a little crazy. It uses triple induction. It uses every parameter. This is how the statement came, because we couldn't do it until we started adding more stuff. I'll skip any notion of how it works. You have to, of course, be careful of how big T is. And for a long time, there's the small case and the large case, but there's this in-between case that's kind of a transition when you're right at the cusp of that threshold that's got some hairy problems. So I'll skip that. We proved more general statements that could be useful for future work about chordal graphs. Turns out they're semi-greedy. I tell you what greedy was, that you could always walk towards the roof, towards the target. Here, this means you never walk away from. So semi-greedy means that sometimes you might walk sideways. You might move to a vertex that's just as far from the target as you started. Didn't get farther away or closer. That's necessary, but it's sufficient. Other things about chordal graphs that we learned, that they have maximum sized, unsolvable configurations in which every big vertex is simplicial. Like on the tree, all those locations of the pebbles were at the leaves, right? So far away. It's a natural notion. We thought this has got to be true. We proved it for stacked targets. It turns out to be false for general ones. We would have had a nice short proof if it was true for that. But it turns out we lost probably months on trying to prove that until we discovered it was false. This is like a 2.5-year result, by the way. There's going to be some champagne flowing when we finish writing it. So there's some nice things. Let me just finish with a couple open problems that if you feel like playing around with some undergraduate students, you've got an REU, or you just have students doing nice projects in your graph theory course or what have you. Look, take 2 targets on a tree. And can you actually explicitly say, we have an upper bound, knowing what the tree is for one target and what the support is, but can you actually get a formula akin to what Chung did to decompose the tree in certain ways? Just 2 targets, try it with, that would be a great one. Here, can you say that if you just have a single target in a chordal graph, can you say that it's always the hardest to reach the simplicial one, just like it's hardest to reach a leaf in a tree? Very natural question. Should be true. But should doesn't get you too far, right? We all know that. Try the target conjecture on some of the other fun starter kits, cycles, cubes, Peterson graphs, these kinds of things. And 2 more. One is, what's the right version in Graham's conjecture? Again, a lot of the motivation for this is strengthening Graham's conjecture enough to make the proof easier. What's the right thing? Is this it? And do you have to maybe also prove a strong conjecture in some form for these products? So that's where the biggest aim is. And finally, play in control, hit a high percentage of 3s, don't turn the ball over. That's maybe the hardest of these problems, but we'll see. Anyway, let me stop there, take any questions you have, and again, thanks for the opportunity to speak to you about this stuff.
Thank you very much, Glenn. I guess, does anyone have any questions that they want to ask the speaker?
I'd like to ask if you've looked at any probabilistic methods for the bounds when you have, my experience in extremal problems is that there's always one bound that's constructive and the other one is usually probabilistic.
Yeah. So that's a great question because yes, we have, and we've never been successful in this model of applying it, but there's a different question. With the same model, you can ask a different question. Here, we're asking for a guarantee, right? How many pebbles do you need to guarantee victory? You can ask, in some sense, it's the worst case, right? How many pebbles can my adversary put down without me succeeding? The best case would be if I didn't have an adversary and I had complete control and I got to take the fewest pebbles possible and distribute them as carefully as possible to be able to reach anywhere I want. I've always thought of like this is owning a cab company in a dangerous city, that you want your cabs distributed to be able to reach anywhere, but you also know that 2 cabs have to go down the street and one of them is going to blow up, right? So that's sort of the best case scenario. There's the average case scenario, right, which we call thresholds, and there's a bunch of good work on that. That you're asking for how many pebbles do you need as an order of magnitude to win with high probability. So that, yeah, there might be some unsolvable configurations, but overwhelmingly the probability tends to 1. And there's a lot of good work on that. And these things are called thresholds. Wrote a paper with Graham Brightwell and Irat Bekhmetev in the 2000s on that thresholds always exist. That sort of stuff. And there's a lot of nice extremal set theory that went into proving that kind of existence. The bounds are tricky for some examples and some are still open.
Yeah,
Cubes, for example, is a hard one.
Very nice talk. Thanks.
Yeah, thanks.
I have a question. So how meaningful do you think if we try to consider the following version of your problem, namely that you don't require you have to stop at a certain target distribution, but rather it's like at some point of your game, you achieve that in a certain vertex, and then you move on. You can move those vertices out of that target vertex to help you get to another one.
Yeah, that's nice. So that, in a sense, that changes the cost by 1, because currently once you've put a pebble there, the person who needs it eats it. It's right there. It's a game of Skittles. Once they got one, they're going to eat it. But what you're saying is let that Skittle continue to be used.
Right.
That's a nice one. I
Right.
think that's a good
So you think
variation.
it's like quite different and not many people study that one? Or is it like easily transformable to a different version, or some people have already studied that?
Nobody has studied that, I know for a fact,
Okay.
at least in published form
Okay.
or raised it at conferences that, yeah. No, that's a nice one because you could see how that in some instances could be the application that helps somebody and be useful. There is an application, a variation also, where the two pebbles you start with don't have to be on the same vertex. They have to be adjacent to the same target. So that means the one moves there like normal, but the other one, the cost can come from somewhere else.
That's right.
The toll, I mean, and that's called rubbling. So little tweaks in this often give, and it's a little bit like in domination theory. There are lots of tweaks of things that you could envision, and there are lots of interconnections between them, right? If you solve this version, that helps you get a bound on that version, and so this would be useful. Yeah, nice one.
Well, thank you.
Any other questions? I just have a very simple one. So does it make sense to consider something along the lines of Graham's conjecture for any other graph products, like for instance, the lexicographic one? Does it make the problem very trivial, or is it?
Yes, actually, so yeah, Franklin Kenter and I just published a paper last year and a half on a couple of different other products for which Graham's conjecture is true. We've also a group of people over the last maybe seven years or so have been looking at approximations too, right? So, and we have some results in that paper as well that an upper bound of twice the product is sufficient. Can you get 1 plus epsilon, right? So approximations of Graham's conjecture, for example, are worth it. Yeah. And for that, probabilistic techniques might come in handy. But I see Andrew's gone, so.
No, I'm here.
Oh,
In
you are
fact,
there. Good.
yeah.
Yeah.
In fact, I wanted to know if I may, could I see the slide again where you had one using the groups where you had the formula 1 over.
Yeah. Oops.
I wanted to read that again.
Oops. I don't want to. But I just want to. There it is.
Right. So you're requiring that she is a billion.
Yes. Yes. That's crucial.
Yeah.
Once you have that it's not a billion, then you're talking about sequences instead of subsets. And the Russian doll analogy doesn't work because the order in which you put them in there matters. And so you can't put them together and get the same sort of results. There's a way to sort of fix that problem, but in so doing, the lattice that you're working on stops being a lattice. It becomes a poset, and then you have other problems. Yeah, nice question. Very true. Although Kleitman's conjecture is it works for all groups, and there's been no hint that it's wrong, but this method just completely halts at that point.
This looks very much, it comes up in genus problems, this 1 over the orders.
Really?
Oh, yeah.
And embedding on surfaces?
Yeah, yes. It comes up in embedding tilings. And for less than or equal to 1, it's probably the hyperbolic plane.
Ah.
Yeah, it also comes up in the algebra. That's fascinating. It's a fascinating formula. That's why I wondered if it will extend it beyond a billion groups.
Yeah. Yeah, be very worth trying.
Great.
All right, I think we're out of time. So if there's no more questions, let's maybe virtually thank the speaker. And thanks again, everyone, for joining in.
Good. Thanks again. Good to see so many of you again and meet a few new ones. Hope to do so in real
Yeah.